welcome to everyone. I'm very happy to have Christian as speaker of our series of seminars. Christian is well known for his important contributions on swarm intelligence and optimization in general fields, with main reference on hybrid metaheuristics. He was and he is a primary speaker in many international conferences, and let me say that he was one of the excellent lecturers of the first metaheuristic summit. He has many disciplinary research collaborations, and some of his research papers are among the most cited. So thank you very much, Christian, for accepting the invitation. And for all participants, if you have any question, click on the raise hand button after the question time. So Christian, you can go with your talk. Thank you very much again.
Okay. Thank you very much, Mario, for the nice introduction and for the invitation to give a webinar in your place. So today I'm going to talk about hybrids. Okay, so you see this title, Are You a Hybrid? Yes, of course, everyone is a hybrid nowadays. This is of course a bit exaggerated, but what I want to say with that is that many people nowadays work on hybrid optimization algorithms without even thinking about it. Okay, so when 20, 30 years ago, maybe people still were working on pure techniques like only on tabu search or only on genetic algorithms or only on operations research. Nowadays, many people make combinations, but they don't even think about it. So it was getting somehow normal that people develop hybrid algorithms. Okay, so this is why I was choosing this title. But let me start by introducing a little bit where I'm working. So I'm working at the Artificial Intelligence Research Institute of the Spanish National Research Council. This is the largest public institution dedicated to research in Spain. The third largest in Europe, I think, after the Italian CNRS probably, and the French one. About 6% of all research staff in Spain work for the CSIC, and we have about 20% of the scientific production in Spain. So of the total, 20% is ours, let's say. So that you see this discrepancy between 6% of research staff and 20% of the scientific production. This is simply because we are not giving classes. Okay, so we are not involved in teaching. We are 100% full-time researchers, if you want. We are one of the small institutes at the CSIC, so we are just 21 tenured scientists of 3 different ranks. And the majority of people here are PhD students, actually. So strangely enough, in this pandemic year, we had the biggest growth of PhD students that we ever had. We still don't understand it, but this is how it was. This made things also a bit complicated because we are teleworking. Basically, we shouldn't come here. Today I'm here, but so incorporating new people is actually quite difficult. We have some main lines of research, which include machine learning, optimization, which is mine, logic and constraint programming, multi-agent systems. Okay, we have also a quite large group on multi-agent systems. Okay, so the topic of today, well, my topic is optimization. The first 3 slides, I just nearly spoke Spanish. Many times I have these slides, even though I know that many of you know these topics, but it's just for preparing the ground. Okay, so it's about optimization. In general, we can distinguish between function optimization, so real valued optimization, and combinatorial optimization. There we have again subclasses, as you know, My work is on combinatorial optimization, okay, and mostly on problems that can be, let's say, modeled as integer programming models, linear ones, or mixed integer linear programming models. You know that combinatorial optimization problems arise everywhere and in numerous industrial settings. So just to pick one example here, so in the middle here you have vehicle routing. Okay, this is one of the most simple cases where you have one depot, you have a fleet, and you have customers. So these circles here, the blue, red, and green ones are customers, and you have to find routes for all the vehicles subject to constraints. Okay. Actually, at the moment, so these problems can be very much complicated, also much more complicated. So at the moment we are looking at with a PhD student at sustainability in these problems. Okay, so we are looking at electrical vehicles, charging stations, and so on. The two echelon structures. So where you have one central depot, you have satellites around. So you have two phases basically where first goods are transported from the central depot to satellites, and then you have to find routes for bringing things to customers. Okay. So on one side we have problems, on the other side we have algorithms, and there we can also make a very rough differentiation between exact techniques. So we have dynamic programming, for example, we have branch and bound techniques. We have on the other side approximate techniques like greedy heuristics, like metaheuristics. Okay, and I guess most of you are working in some way on metaheuristics, so you know what evolutionary algorithms are, unpooling optimization, taboo search, and so on. My work is mostly on the overlap between the two. Okay, so we are often making use of exact techniques within approximation or approximate techniques, but we are not developing specialized exact techniques for these purposes. Okay, so our algorithms, our work is mostly algorithm oriented. Okay, so many times we don't have a specific problem, but we want to make rather advances on the algorithmic side that are useful for many different problems. Okay, moreover, we assume that for example, if a company would like to implement something like this, they will never be able to develop a specialized branch and bound approach, for example, or even something more complicated for their problem. So what we are using is generally on the exact side, we are using solvers like Simplex or Gurobi. Okay, so you don't have to know anything about the exact side, because you just have to know how to model your problem for these solvers. Okay, and then the solvers, they solve these sub-problems that you define within your metaheuristic, let's say. Okay, so this is the hybrid metaheuristic side. This is one of my pillars or lines of research. The other one is swarm intelligence, what Mario has already mentioned. This is not a topic of today's talk, but I want to go quickly into this subject, just to tell you what we are doing and what we have been done in the last years. So if you are interested in some of these topics, you can look them up in our papers on our websites and so on. So swarm intelligence, if I would have to say that in one sentence, it's an AI, artificial intelligence discipline, whose goal is designing intelligent multi-agent systems by taking inspiration from the collective behavior, this is important, of animal societies, such as ant colonies, flocks of birds, or fish schools. Okay, on this slide you have three examples. On the left here you have a termite nest. So these nests, they can be very high. So this one looks like it is 5 or 6 meters high. They have an incredibly complex internal structure. So there are rooms or chambers in there. which have the same temperature all over the year, for example. Okay, so they have a very complex system for guiding air streams through this nest. But the termites, of course, they don't know how to build that. Okay, so this is a result of the termites following a set of simple local rules. Okay, these have evolved over time. The same we can say about this V-shaped behavior of birds. Okay, so migrating birds, they are usually flying in this V shape, which is also a result of following simple local rules. And this has evolved over time for a specific reason. The reason is that like this, as a flock, they can save energy. Okay. Okay, on the right, you have a fish school. For sure, you have all seen something like this, at least on TV. They are all, when predators are approaching such a fish school, they are getting very close together, moving basically very fast, all at the same time. They look like a single organism. And the reason why this has evolved is that it's a protection against predators. Okay, when a predator sees something like this, and it's difficult for the predator to pick an individual fish. Okay. So when we look at these swarm intelligence systems, we can see that they consist of a set of simple entities. They are distributed. There's no kind of global control. Actually, biologists until the 50s of the last century, they still thought that, for example, in beehives, you would have the global control by means of the queen. So the queen would be giving orders, but this has turned out not to be true. They are based completely on self-organization, which is a result of different ways of communication. So on one side, we have the direct communication here, which can be by visual or chemical contact. On the other side, and this is the important aspect for swarm intelligence, we have the indirect communication, which is often labeled stigmergy. Okay, this term was invented by a French biologist called Grasset in 59. Okay. So this graphic here shows you how these systems solve problems. Basically, E means the environment. Okay. The sub-index means that the environment is in a specific state. And R means response. Okay, so the environment being in state 1, let's say, triggers a certain response of the colony. This changes the environment, which in turn triggers a different response, and so on. Okay, so in this way, for example, the termite nest is built. And in general, we can say that complex tasks can be, I'm sorry, can be accomplished in cooperation. Okay. We've been working on different swarm intelligence topics over the years. For example, at the moment, we are working in, again, in combinatorial optimization. The main topic of one of my current PhD students is adding negative learning to uncolony optimization. Okay, uncolony optimization basically is based on positive learning, positive feedback. So the algorithm is generally learns from positive examples. Okay, so you're using good solutions for making the pheromone update. But in nature, we see also examples of negative learning, and this is we try to incorporate this into uncolony optimization. And in fact, we have just won the best paper award at the ANS conference. I don't know if you have seen me on camera. So we won this very nice ant, which is from bronze. Very nice thing. Okay. The second topic I want to mention is this is already a couple of years, 3 years old. We have been working on distributed optimization problems like this distributed graph coloring. And there we have made use of the self-desynchronization that you find in Japanese tree frogs. Okay, so in these frogs, the males, make crocs, and the females, based on these crocs, decide which male to approach. So when two males that are heard by the same female croak at the same time, or very close in time, and the female cannot distinguish their croaks and cannot distinguish any direction. Okay, so over time they have evolved a system to desynchronize their croaks, and we have made use of that for distributed graph coloring, for example, or independent set finding also. Another topic I want to mention is duty cycling in sensor networks. So in sensor networks, we have small devices that are generally powered by batteries, and they have to measure something, for example, every now and then. And one mechanism for energy saving is that they are switched off periodically. Okay, and we have devised a self-organized system for doing so, which is based on the sleep-wake cycles that are observed in ant colonies. Okay, so if you want to know anything more about these topics, you could have a look at my webpage. But now let's go on with the real topic of this talk today, hybrid metaheuristics. So first of all, what is a hybrid metaheuristic? The problem is that there is not really a precise definition. Okay, so there is no clear line where we can say this is a hybrid, this is not a hybrid. We can give a possible characterization. We can say it's a technique that results from the combination of a metaheuristic with other techniques for optimization. And what is meant by that, by other techniques for optimization, we might use another metaheuristic. Okay, so we might use one metaheuristic inside another one for certain tasks. We might use operations research techniques, dynamic programming, and so on. But what is their reason of being? Okay, so generally, when we have a problem that we want to solve, it's not always the same, but generally this is what happens. Okay, so with growing problem instance size, first, for the small instances, exact techniques are usually very good. Okay, CPLEX is very strong for many problems when you have rather small problem instance sizes. But then you have a kind of a phase transition when the problem instance size grows, and at some point you have to resort to approximate techniques like metaheuristics. But then at some point, also these search spaces of very large problems might be too large, so metaheuristics might be lost. And then we can exploit synergies between exact and approximate algorithms for getting an algorithm that works reasonably well for large-scale problems. Okay. So a bit of history. For a long time, different communities in optimization, they have been quite disconnected from each other. Okay, so everyone was working on its own technique, not looking very much on what the others were doing. Hybrid approaches in the 90s, they appeared already, but this was quite sporadic. I would say about 20 years now, the published body of research on hybrids grows. This can also be seen by the starting dates of these conferences. Okay, CPAI-OR, which is nowadays quite a very well-known conference in this field. The Math-Heuristics workshop, which is a bit smaller. We also had a workshop series on hybrid metaheuristics. But as I said before, when I was talking about the title, I think nowadays many people work on hybrids, and maybe we don't need specifically dedicated conferences to hybrids. So we basically stopped with this workshop series. Okay, so before I want to give you an example of our own work, I want to go into, I want to show you some examples of other people, okay? Some interesting examples, just to give you an idea of what kind of hybrids are out there. Okay. So first of all, I want to talk about decoder-based approaches. Okay, the general idea of these approaches is that we represent feasible solutions in an indirect way. Okay, and then we have a decoder that takes such a solution, represented in an indirect way, and translates it into a real solution of the problem. Okay, so advantages of this approach are that like this, we can transform a complex, possibly complex search space into one that is much easier to handle. So we could, for example, move problem constraints into the decoder. Okay, so our metaheuristic doesn't have to handle with some of the constraints, but the decoder does. This is actually quite often done. Note also that this type of algorithm, even though it's not called a decoder-based approach, this is very well known in evolutionary algorithms. Okay, so for a prime example are biased random key genetic algorithms. In these algorithms, solutions are basically represented as strings of real values between 0 and 1. And then a decoder would translate such a solution, for example, into a scheduling solution or in whatever problem we want to solve. Let me give you a very nice example. This is already 12 years old, but it's a very nice example of a decoder-based approach. So in this example, this is called generalized minimum spanning tree problem. Okay, so you have a fully connected graph. Every circle here is a node of the graph, and the nodes are clustered. Okay, so in this case, we have 5 clusters that contain together all the nodes of the graph. And between each pair of nodes, we have a distance. Okay, so we have to find one node from each cluster, and we have to design a spanning tree among these nodes, such that the sum of the distances on the edges that I've chosen is minimal. Okay, so basically there are kind of 2 phases. Okay, in this problem, which nodes do I choose from the clusters, and then how do I connect them with the spanning tree? So in this paper that I just showed you or referenced on the slide before, they considered 2 options of decoder-based approaches. In the first option, they define a feasible solution as a set of nodes which contains exactly one node from each cluster. Okay, so their metaheuristic only looks at sets of nodes, doesn't care about spanning trees. Okay, and then we obtain an actual solution from such a solution by applying Bream's algorithm. Okay, to a feasible solution, to such a subset of nodes. In option 2, we define a feasible solution as a spanning tree of the clusters. Okay, so here solutions are spanning trees, but it's not fixed yet which node from each cluster is actually chosen. Okay, and the decoder uses an efficient dynamic programming algorithm that, given such a spanning tree on the clusters, chooses the best nodes possible from each cluster. Okay. Okay, the second example, so this was decoder-based approaches. Second example are multi-level frameworks. They exist since quite a long time, but they're not often used actually. I think it's really a pity. We have done some works already on multi-level frameworks, and sometimes it doesn't work, but we had cases where it was working really well. So the general idea is that first we have a problem instance, okay, and then we do an iterative coarsening of the original problem instance. This means we make it iteratively smaller. At some point we stop and we try to find a solution to this coarsest level, to this somehow reduced problem instance. And then we go step by step again back to the original problem instance by refining always the solutions that we have. Okay, so this is shown in this graphic here. This is the original problem instance. We make it iteratively smaller and smaller. We stop here. We apply a metaheuristic. We get a solution to this small problem instance. Then we expand the solution to the next level. We might again apply our metaheuristic to refine the solution and so on. At the end, we have a solution to the original problem instance. Okay, so just to show you that these techniques are very much used nowadays. So these are two examples, recent examples. This is from 2020, and this one is from I think it's from 2019. Don't see it now. Looking at the titles, this gives you already the idea that many times graph-based problems are tackled with this kind of framework. Okay. So the third example I want to talk about are combinations with machine learning. Okay, so this is very, very hot topic nowadays. Many people try to get into this topic. So you know that in artificial intelligence we have different lines of research, and one of them is machine learning. So there it is about algorithms with the ability to learn without being explicitly programmed. Okay, and deep learning, which is one of the latest developments there, has changed, for example, very much our ability for image recognition and things like that. Okay, and they use different types of neural networks. I've just put two possible ones here that are often used: recurrent neural networks and convolutional neural networks. They are used in deep learning. Actually, there's a very nice survey paper from this year by Bengio, Lodi, and Provost. And they give a very nice overview on what type of combinations we have at the moment between combinatorial optimization and machine learning. And they say that machine learning can basically be used in two different ways, okay, for improving algorithms for combinatorial optimization. The first one is to generate a fast approximation for heavy computational tasks. Okay, so for example, if you think about an objective function which takes a lot of time to compute, okay, then maybe we can use machine learning or deep learning to get a fast approximation for at least a subset of the problem instances which have somehow similar characteristics. Okay. The second one is learning missing expert knowledge. So there are problems where we really don't have good greedy functions, for example. Okay, so we want to generate solutions step by step, but we don't have a good greedy function. They are all very deceiving, for example. So we could try to learn greedy functions, and this is actually done in this example paper that I've put here. Okay, from 2017. There have been other papers in this style afterwards, but this is one of the first ones which does that. Okay. They have used a deep learning architecture which is called structure to vec, and they use a Q-learning type of Q-learning for training this neural network, and they have used that to learn 3D algorithms for problems like minimum vertex cover, maximum cut, traveling salesman, and they could outperform existing greedy algorithms in this way. Okay. The nice thing was also that they could generalize to different problem instance sizes. So they could learn, for example, with graphs of size 100, and it would still work for graphs of size 500. Okay. So this was also another nice aspect of this work. Just have a look at the time. Okay. So just to tell you one example of a problem where the greedy functions that we have are not good. This is the capacitated minimum dominating set problem. This is a problem where we really don't have a good greedy function. Okay, this is a variant of the well-known minimum dominating set problem. Okay, so the classical MDS, minimum dominating set, asks for finding the smallest subset of nodes in a given graph, such that each node of the graph either forms part of this subset or is a neighbor of at least one node in the subset. Okay, so this solution here, so we just take this node. This is the optimal solution in this graph because all the nodes, all the remaining nodes are neighbors of this node, so we have a feasible solution. Okay. The capacitated minimum dominating set problem has another restriction. Okay, so here the restriction is that each node can cover at most a certain number of neighbors. Okay, here this node is covering 8 neighbors, but we might have the restriction that each node can only cover 2 of its neighbors. Okay, so if each node can only or maximally cover 2 neighbors, then this is the optimal solution we can get. Okay, choosing V4, V5, and V6. And the bold lines here show you which neighbors they cover. So here we have two phases somehow. So when we construct a solution, we have first to choose which nodes belong to the set. And in the second phase, somehow we have to say which neighbors these solutions cover. And especially for the second step, there are no good greedy functions. Okay, so with one of our PhD students at the moment, we are trying to learn to train a neural network such that, or to learn a greedy function. In other words, okay. Okay, now let's move to our own work. And this example I will outline in a little bit more detail. Okay. So first of all, I'm going to explain a specific algorithm that we developed some years ago, also in the context of a PhD thesis. And to make things simpler, I will explain it in the context of subset selection problems. Okay. Many problems are actually subset selection or can be phrased as subset selection problems. So in this kind of problems, we have given a finite set of items, C. So 2 to the power of C is the set of all subsets of these items. Okay, so we have a function for each of these subset problems. We have, or subset selection problems, we have a function that tells me for each subset of the items if this is a valid solution or not. Okay. And then we have an objective function, which we might want to minimize or to maximize. Even the TSP can be seen as a subset selection problem, okay? Because if we say C is the set of all edges of the TSP graph, then all the subsets of this set whose edges form a Hamiltonian cycle in the graph are feasible subsets, okay? So before I explain our own algorithm, I also want to explain large neighborhood search, which is also probably the most known hybrid technique. So if we do neighborhood search, first of all, we have to decide on the neighborhood that we will be using, and this neighborhood can be small or large. What does that mean? So a small neighborhood means that every solution has only very few neighbors, and with a large neighborhood, I refer to neighborhoods where each solution has a lot of neighbors. And there are advantages and disadvantages for each case. Okay, so when I choose small neighborhoods, the advantage is it is fast to find an improving neighbor because each node has each solution has just very few neighbors. The disadvantage is that the average quality of local minima is quite low in this case. When I choose large neighborhoods, then the advantage is that the average quality of the local minima is high, but finding an improving neighbor might itself be an NP-hard problem. Okay. There are different ways of examining large neighborhoods. We could do that heuristically, or we could use an exact technique. For example, we could use an ILP solver if we can phrase this problem of finding and improving, or even the best neighbor of a solution as an ILP. And this is the flow chart of large neighborhood search, of destruction-based large neighborhood search. There are many different variants of large neighborhood search, but this is one which is very often used. Okay, so we generate an initial solution S in some way with a greedy heuristic, for example, and then we repeat in each iteration the following 3 steps. Okay, so first we destroy the solution partially. This gives us a partial solution, and then we apply an exact solver requiring that it finds the best solution that contains this partial solution as a sub-solution. Okay, so this solver returns a solution SILP, and then we can choose between S, so this was S here, between S and SILP for being the solution for the next iteration. Okay, we might choose different criteria there for deciding. Now we developed an algorithm that is somehow in a similar line as large neighborhood search, but it's conceptually quite different. Okay, it's called construct, merge, solve, and adapt. The main publication is this year. This was published in 2016 in Computers and Operations Research, and the results that I want to show you are from this paper, which is published next year, but which was already available in August 2020, okay, of this year. Okay, so this algorithm for subset selection problems works as follows. So C, remember that C is the complete set of items. C prime is a subinstance, which is initially empty, okay? And then all components in C, or all items, have also an age, and this age is set to 0 at the beginning of the search. Okay, and then at each iteration we are iterating these 4 steps here. So first we probabilistically generate a number of NA solutions, okay, and we merge all the components that we find in these solutions into a set C hat, okay. Then we add C hat to C prime, which is our subinstance. Okay, C prime is initially empty. So if we go into the first iteration, then this would be the first addition to C prime. Okay, so the components that we found in the NA solutions generated in this iteration. Then we we apply an exact solver, telling the solver that every solution can only contain items from C prime. Okay, so in a sense, if we are in the first iteration, we are looking for the best solution that we find in the merged subinstance, in the subinstance that we get by merging all the solutions generated in this iteration. Okay, so this gives us a solution SILP. After that, we increment the age of all components in C prime, and afterwards we set the age of all components that are in the best solution to the subinstance to 0. So this means somehow they are useful. Okay. And as a last step in each iteration, we are removing from C prime all the components whose age has reached an upper limit. Okay, this is also a parameter of the algorithm. Okay, so if there's a component in a subinstance that never appears in the best solution, then after h max iterations, its age has reached the limit and it's kicked out of the subinstance. Okay, this simply means it's not useful. So this is the algorithm, and we have applied that to many different problems. But in this last paper, one of the problems was the multi-dimensional knapsack problem, but the goal was not to find a new state-of-the-art algorithm for the MDKP. The goal was more to compare LNS and CMSA and to see the differences and the things they have in common. Okay, but I will show you also comparison to the state-of-the-art. So this problem, which is very well known, is one of the very well-known test cases in combinatorial optimization. We have a set of items C. We have a number of we have a number of M resources. Of each resource, we have a maximum quantity, the capacity CK. Okay, and each item requires from each resource K a certain quantity RIK. Okay, so if I choose item A for my solution, and this requires this amount of resource from resource K. And each item I has also a profit PI. Okay, so valid solutions are subsets of the set of all items, such that the sum of the resource requirements for each resource is mostly the capacity, okay, of this resource. Doesn't exceed the capacity, let's say it like this. And the objective function to be maximized is the sum of the profits of the items that are in my solution. So for applying LNS and CMSA, all we need is a greedy heuristic. Okay, in the case of LNS, we use this greedy heuristic for generating the initial solution. And in the case of CMSA, we use this greedy heuristic in a probabilistic way for generating a number of NA solutions at each iteration. Okay, so actually we don't have to get into this heuristic. It's a very simple one. The second thing we need, the second component, both for LNS and for CMSA, is an ILP model. Okay. And this is the very standard ILP model for the MDKP. We have a binary variable for each item. We maximize the sum of the profits of the taken items, and these are the constraints that such that the solutions respect the resource capacities. So in LNS, when we have a partial solution, we apply this model, but we add additional constraints. So we fix all xi to 1 that are in the partial solution. So this means these items, they have to appear in any solution. And in CMSA, we simply replace all appearances of C here with C prime. Okay, so this means we only allow that the ILP solver chooses items from C prime. Now, when we generate instances for the MDKP, the main characteristic, let's say, of instances is the instance tightness. So I can have very tight resource capacities, very low resource capacities, and this means that in this case, my solutions will be rather small. Okay, so only very few items will fit into the knapsack. So when this tightness grows, okay, so when the resource capacities increase, then I get solutions that are every time larger. Okay, and there's this alpha parameter. So there's an instance generator, and it has this alpha parameter between 0 and 1. And 0 would mean that the resource capacities are 0. 1 means that are maximal. Okay, and we can vary. We can set that to everything in between. Okay, so for a small alpha close to 0, we would get problem instances where solutions are rather small. And then in this paper that I showed you from this year, we applied both LNS and CMSA to instances from the whole tightness range, because our intuition was that CMSA should be better for, in general, not only for this problem. That's why we considered several different problems. So that CMSA would be better for problems where solutions are small. Okay. So both algorithms, they are of course tuned for every specific tightness range and so on. Now, these are results for instances with 500 items and with 1,000 items. And on the x-axis of these two graphics, we see different values of alpha. Okay, so this first box plot here are results for alpha equal to 0.1. So here are problem instances with small solutions. So when we move to the right here, we get problem instances where solutions are increasingly large. Okay. And these box plots, what they show is the improvement of CMSA over LNS for, I think it was 50 instances. Okay. So every dot of these is the result for one of these instances. So if this box would be in the gray area, so greater than 0, then CMSA would be better than LNS. Okay. If this box is in the white area, then LNS is better than CMSA. We see that, actually what we see is that for instance sizes of 500 and 1,000, there are no differences between CMSA and LNS. Okay. Now, when we move, sorry. This doesn't move. Let's just wait for a second. I think these images are very large. Okay. Okay, this is the slide. So these are the graphics for instances with 5,000 items and 10,000 items. And there we see our intuition confirmed, let's say. Okay, so for the problem instances with rather small solutions, we see that CMSA is better than LNS, and at the end they are basically behaving the same. Okay, and we can see the same for instances with 10,000 items. Another aspect of this work was to study somehow the behavior of algorithms in a comparative way by visualization. Okay, so we developed actually a tool in order to visualize algorithm behavior in a comparative way. Okay, so here we have blue are solutions visited by LNS. Okay, orange are the ones by CMSA. This is just an example. Okay, there are 3 runs of each algorithm. Okay, you see that the 3 LNS runs, they start from the same greedy solution. Okay, and the CMSA runs, they start from different random solutions, if you want. And then you see the search trajectories. Okay, so we can see that there seems to be an attractor. Okay, this is green means that it was visited by both algorithms. So both algorithms seem somehow attracted by this solution, and this is the global best. Okay, red is the best solution, not the global best, the best solution found across all runs and algorithms. Okay, so we can see different things here. We can see that CMSA trajectories are shorter, much shorter than LNS trajectories. But again, this is only an example. Okay, so let's have a look at visualizations for the MDKP. Okay, so blue is again LNS and orange is CMSA. This is for an instance with 10,000 items and for low tightness. So solutions are small. And this is for 10 runs for each algorithm. Okay, we see that for this type of instance, LNS actually seems to be lost. Okay, so there's no overlap between the different trajectories of LNS. They all end up in different points, and there's no overlap between LNS trajectories and CMSA trajectories. On the other side, CMSA trajectories seem to have attractors. Okay, so there seems to be an attractor in the search space that attracts the CMSA trajectories. But the best solution actually was just found by one of the runs. So if we go to medium-sized instances, not medium-sized instances, instances where solutions are of medium size, then the picture changes. Okay, we see some of the CMSA trajectories are actually lost also. We see overlap here, so there seems to be an attractor that attracts most of the, or many of the LNS end of the CMSA trajectories. Okay. But again, the best one is really found by one of the LNS trajectories in this case. Here, the trajectory lengths are basically the same. Now we go to, we see also an example for the case where solutions are large. Okay. Here, LNS is even more, CMSA is even more lost. Okay, we see 1, 2, 3, 4, 5 trajectories that have no overlap with the others, and only the other 5 converge, if you want, to some common attractor. Okay. So these graphics, they tell us something about algorithm behavior. So when we first submitted this work, we didn't actually compare to the state of the art, okay? Because first, it was not our goal, and second, the MDKP was used as a test case for so many years that we actually didn't think that there's a chance that we beat the state of the art. Okay, so these are the 2 best algorithms as far as I know at the moment. This is they are quite complex. Okay, so this is a 2-phase tabu search algorithm. This is a particle swarm optimization algorithm with different additional mechanisms. They are quite involved algorithms. And we compare to them. Okay, here I just show you a comparison for the 30 instances with 500 items and 10 resources from the OR library. Okay, so there's a very well-known set of benchmark instances for this problem on the OR library. And the common practice in this set is that people apply the algorithm 100 times to each instance. Okay, so here I show you average solution qualities over all 100 runs and all 30 instances. And you can see that CMSA is actually slightly better, even though this is probably not statistically significant, than the 2 state-of-the-art algorithms. Okay, so we can say they are on the same level. A good aspect is that our algorithm is quite fast. Okay, so surprisingly for us, we are on par with the same level with the state-of-the-art, and the algorithms are much simpler. Okay, so these are really simple algorithms that you can implement in I don't know, 200 lines of code. Okay, so this with this I want to finish. Let me just summarize a little bit what I've told you today. So I've told you about hybrid metaheuristics. Their reason of being is especially in the context of large-scale problem instances, also real-life problem instances, if you want, even though this is not our own research topic. So as I said, we are basically focusing on algorithmic advances. The advantage is that they profit from synergies between different techniques. As I said, my title is a bit exaggerated, but many algorithms nowadays are in some sense hybrid. Okay, there are of course many different possible research directions. You might contribute to a deeper understanding of existing approaches, or especially in the field of combining machine learning with combinatorial optimization algorithms. I think there's quite some room for actual new developments. Okay, here are 2 books. Probably most of you know the first one. This is already the 3rd edition of this book, which is I think it's a very good. It's the edited book, but it's very good chapters, I think, about all kinds of metaheuristics. And the second one is a book about hybrid metaheuristics that my colleague and I, Günther Reidel, we published that in 2016. Okay, with this I want to finish for today, and I hope you can take something home, and if there are any questions, I will be happy to answer.
Okay, thank you very much, Christian, for your excellent talk as usual. Thank you again. Any question? Yes, Carolina.
Yes, good afternoon. Thank you, Professor Blum, for your inspiring talk. I have maybe two naive questions. I am looking at my notes that in particular are just photos of my screen. The first one is about the phase transition you mentioned in the first at the beginning of your talk. I have a master in physics, so when you talk about phase transition, I'm used to talk about phase transition in a more physical terms. You say that we can consider like a phase transition between the exact techniques or the approximate techniques. And I don't know if you know that in physics there are two different kinds of phase transition. The phase transition of the first order and the second order, and you know that these kinds of transition happens when there is a change in something, in some variables. For example, the temperature of phase transition between water and ice. Maybe we can say that is the same in the phase transition between the use of exact techniques and approximate techniques, and if it is related also not just about the problem instance size, but also on the problem instance complexity. Because I know that the more complex is a problem, the less you can use exact techniques.
Yeah, so of course I didn't use the term.
I know.
In the physics sense. What I wanted to say with this term is that when you use a tool like Cplex, okay, or Gurobi, for Gurobi is the same, interlinear programming solvers, okay, then they work really well up to a certain problem size when the performance suddenly and strongly starts to degrade. Okay, so this is what I refer to with phase transition. So you might have some problem with a specific size, and you might get still the optimal solution in a very short time. But then, if you increase the size of the problems just a little bit, you might end up very far from the optimum and with a very large gap. Okay, and this is usually done. I mean, this happens in a very small spectrum of instance sizes or instance complexities also. Okay. I was using size here as one example of a measure which you can use to differentiate between problem instances.
Okay. The other question was about the example of multi-layer framework, because you say that the general idea is to coerce the original problem instance to find a solution to the course's level, and then refine the solution at each level. But if I look at the image, I can see that it is similar to the divided et imperor method, and how can you be sure that in the phase of constructing the problem you take into account the best characteristics of the problem, because it's a risk, it's dangerous to split the problem without taking into account the main feature of your problem. And so how can you be sure, what is the method then to expand the solution at the smallest level from the large to the larger, sorry, to the largest?
Okay. Yeah, of course, coarsening is a risk. Okay.
Oh, okay.
So you might, for your problem, you might find different ways of coarsening the problem, and one might work and the other one not at all. Okay.
Okay.
So if you think about a graph-based problem, for example, okay, you could imagine, okay, we have an input graph, and let's say in each iteration for coarsening, you might choose a maximal matching in this graph. Okay, so a set of edges. Okay.
Okay.
And then you might join the two nodes of each edge into one node for the next more coarsen level. Okay.
Okay.
This decision, of course, is very important. And if you don't use appropriate criteria for this decision, your method will not work.
Okay.
This is actually the main point in this type of techniques.
Okay. Okay. Thank you so much.
Okay. Thank you.
Thank you. Other question? No other question. Okay, so thank you very much, Christian.
Thank you, Mario,
for this very, very interesting talk.
Okay.
So thank you very much to everyone for attending this seminar, and see you in the new year.
Yeah, I wish everyone a nice Christmas and Happy New Year, as far as this is possible. Let's hope next year things are improving.